Hello, in this video we'll do a couple examples on solving things that are exact equations. Okay, so our first example here, sorry, example 1, we're going to show that the equation 2xy squared plus 2y plus 2x squared y plus 2xy prime equals 0 is exact, and then find the general solution. Okay, so kind of following the notation in Paul's online notes, we have two multivariable functions. The first one is that guy, and then n is the piece that has y prime on it. Okay, so the idea is to check that these are exact, we need to take some partial derivatives. We're going to start by taking the partial derivative of m with respect to y. Okay, so treating x like a constant. The first term has y squared, so we're going to bring that 2 down and leave it like that. And then if I differentiate the second one with respect to y, I get 2. And then I'm going to come over here and do the same thing for n, except with respect to x. So now y is a constant, so I have x squared, bring down the 2. And then the x goes away. Okay, so these guys are equal. Okay, so these two things are equal, which means it's an exact equation. Okay, so what that means then is that it's possible to calculate a function. So big phi here, this exists such that the partial of this thing with respect to x is equal to m, which again was 2xy squared plus 2y. Okay, it's a real common mistake to copy the m sub y, or the partial derivative, from the previous step here. Make sure you don't do that. And not only is that derivative equal to that guy, but the y partial of it is equal to n, which is 2x squared y plus 2x. Okay, so now I'm going to do a technique that's slightly different than the one that that Paul does. There's a couple different ways to approach how to do this. One is to integrate one, differentiate, and then set it equal to the other one, which is the way that Paul does it. I'm just going to integrate each of them and then compare the answers to each other and see what those functions of integration have to be. Okay, so I'm going to take this guy, I'm going to integrate with respect to x to undo that partial derivative. Okay, and if I do that, I'll get x squared y squared plus 2xy. And then I'm integrating with respect to x, which means that I get an integrating constant that's a function of only y. Okay, the other letter. And then over here, from this equation, I also have that this thing is the integral of this dy. Okay, so integrating this with respect to y, I'll get x squared y squared plus 2xy, and now I'll have a constant of integration, which a function of integration, sorry, that is purely a function of x. Okay, so we have these two equations, we integrate them, and what that says is that the function itself, phi, has to be equal to both of these things. Okay, so these things have to be the same thing. All right, so comparing them, there's a whole bunch of different ways for these two things to be equal depending on what we choose for those integrating functions. Okay, you can pick anything you want. All right. All that matters is that you find a solution. Okay, so they'll be equal. They'll be equal if we choose. And in this case, notice that I can choose each of them equal to the same thing, 0. Okay, or any constant, to be honest. So there's, yeah, okay. So if I choose them both equal to be 0, then what I have is that big phi is x squared y squared plus 2xy. Okay, so the solution, the general solution, is big phi, is equal to a constant. So it's x squared y squared plus 2xy equals c. Okay, and that's the general solution. All right, so anyway, now would be the time that I would use a initial condition if I had one. It's possible to solve this for y. Paul's online notes goes through tons of ways. The left side is quadratic in y, so it's possible to use the quadratic formula to write this as y equals some stuff. Okay, that's unnecessary at this point. But if we had an initial condition, then we would kind of want to do that. Okay, and that's what we're going to end up doing in the second example anyway. Okay, so now we're going to look at our second example. It's a little bit harder than the last one, and we're also going to find the interval of validity since we have an initial condition. Okay, most of this problem is going to be focused on the interval of validity, but I wanted to do at least one example of actually solving another one of these equations. So anyway, it's good habit to check if these things are exact to begin with. Okay, so we'll differentiate this with respect to y as 1. If I differentiate this with respect to x, I also get 1. Okay, so they are exact. Okay, so that's good. So then I have phi of xy. The x derivative of this is this thing. And also the y-th derivative of this thing is, and I'll just distribute this now because it's going to be irritating otherwise. Okay, so so this means that big phi is equal to, now I'm going to integrate with respect to x, so I'll get 3x cubed plus xy minus x plus that function of integration. And then over here, I'll get, let's see, minus 2y squared plus xy plus the constant of integration with respect to x. Okay, now, unlike the last problem I did, here we can't choose them to be constants, so we have to compare the two things. So these will be equal if, so what I'm going to do is I'm going to look, the h of x has to be the x-only terms on the other side. So it's going to be 3x cubed minus x, and the k must be the y-only terms on this side. Okay. Technically, you could also add any constant to both of these things, and you'd be fine. So if I, to each h and k, if I also said plus 1, that would be okay. But there's no need to put in extra terms when they're not there, so it's kind of understood that you always choose this stuff plus 0, okay, is the constant part of it. So that means that putting this all together, for instance, if I look at the first formula, and then k was minus 2y squared. Okay, so the solution, the general solution, is this thing equals constant. Okay, so that's good. And now I have that initial condition. So let's recall what that was. It was y of 1 equals 0. Okay, so we're going to apply that now. So we have 3x is 1, y was 0. Okay, so I have 3 minus 1 equals c, so c is 2. All right, so the particular solution is 3x cubed plus xy minus x minus 2y squared equals 2. Okay, now this is the implicit form of the solution. So what we can do now is use the quadratic formula. Okay, since this is quadratic in y, we can use the quadratic formula after rewriting it a little bit to put this in its explicit form. All right, so let's just highlight this. This is implicit. Okay, so now I'm going to rewrite this. So there's the y squared, there's the y term, and then the constant, air quotes around that word, term is this. And remember, in order to use the quadratic formula, that side has to be 0. Okay, so now by the quadratic formula, this is minus b plus or minus the square root of b squared minus 4 times a times c all over 2a, which is minus x plus or minus. Okay, so here's minus 4. So this is x squared plus 24x cubed minus 8x minus 16. Check my algebra there. Okay, so simplifying a little bit more. Cancel those negative signs. And then write this in descending order. Okay, so let's come back here. We have two roots, the plus and the minus. We do need to pick the one that works with our initial condition, even though we already used the initial condition. So let's check. Check. That's okay. Y of 1 equals 0. Okay, so y of 1 is 1 plus or minus 24 plus 1 minus 8 minus 16 over 4. Okay, so we need the negative 1. Negative root. Okay, not the positive one like that last example we did. So the particular solution in its explicit form is x minus, now, this stuff. 16. That square root in front of it. There we go. All over 4. Okay. So that was kind of a lot of work. Now we're going to go to the interval, which I can't apparently spell real well. Okay, here, I'll put this in blue. Interval of validity. Okay. Well, right off the bat, just looking at our solution here, we need to have 24x cubed plus x squared minus 8x minus 16 greater than or equal to 0. Okay, so that's something, technically you can solve this by hand, there is actually a formula to, like the quadratic formula for the cube roots of something. Uh, Obviously, you're not expected to know that, though, since it's pretty nuts. But we're going to use a MATLAB to do that in a second. What I do want to do is kind of discuss some graphical significance of this guy. Okay, so let's come back up to our implicit equation here. Okay, here we go. So the idea, looking at this guy's going to be defined everywhere. Okay, it's a curve, and it is clearly a polynomial curve. Okay, it's polynomial in all its things. I can put in any numbers I want, and it's always going to be defined. That's not a problem. Okay, the problem is kind of having to do with this plus or minus. I mean, it has a lot to do with the plus or minus thing. So I'm going to kind of bring this back to the original equation, and kind of give you like a graphical interpretation. Okay, so this is like graphical interpretation. Okay, and then I'll kind of bring this back to something that you have seen before after we do this. So here was the original differential equation. Okay, what I'm going to do is the key is that interval of validities require kind of two things. First, it's an open interval where the differential equation is defined and has a solution. Okay, the key there is, well, you'll see in a minute. Okay, so it's not enough for the solution to be defined there. Okay, that's really important. We're solving a differential equation, so not only do you need the function to be defined, but it has to be differentiable there. Okay, and that's the key, is that the interval of validity requires this function to be defined, which is part of that stuff being greater than 0, but it also means that it has to have a derivative there. Okay, and that's the part that's really going to get us. So what is the derivative? Well, according to this equation, the derivative is this guy. Okay, so this solution is going to be differentiable everywhere except, okay, so this, the place where it's not differentiable, i.e. where y prime is not defined, so y prime not defined at y 4y minus x equals 0, or when y is 1/4 of x. Okay, now, what does it mean for the derivative not to be defined somewhere? Okay, well, okay, let me backtrack. There's a ton of reasons why a derivative won't be defined, but we want to think back to this thing. This is this implicit form here. It's a curve that's polynomial. It's smooth, okay, because it's polynomial. All right, it's smooth and it's defined everywhere. So what are all the ways something cannot be differentiable? Well, if it's not defined somewhere, it's not differentiable. Okay, if it's not continuous, that's part of that. But what if it is continuous there? Okay, the only places where it's not differentiable have to do with corners. Okay, but this won't have a corner because it's a smooth curve. It's a polynomial. So the only other thing to think about is, now in 1D, it's a cusp. Okay, but the way that you think about a cusp in derivative speak is having a vertical derivative. Okay, i.e. the tangent line or a vertical tangent line. The derivative becomes infinity. Okay, and that's precisely what's going to happen if I put 0 in the denominator of a fraction. You get infinity. So now that I know the condition here, I'm going to take this condition and use it with my solution. Okay, so the maybe I need to figure out what that implicit solution was. Okay, so here it is. Memorize it real quick. Okay. Let's hope we did. It was 3x cubed plus xy minus x minus 2y squared equals 2. Okay, so now let's replace all the y's with 1/4 x. Okay, so I'm going to now simplify this. So 3x cubed here plus 1/4 x squared minus x minus, so 1/4 squared is 1/16 times 2 is 1/8. X squared, I'll move this over here just to kind of set up what I'm doing. Then we'll do some more work here. The 1/4 minus the 1/8 is 1/8. X squared minus x minus 2. Okay, and then I'm going to multiply everything by 8 to cancel that fraction out. So here I have 24x cubed plus x squared minus 8x minus 16 equals 0. Okay, and lo and behold, the result that I get is precisely the kind of stopping point of this guy, the roots of this guy where it's going to switch from positive to negative. Okay, so really the interpretation here is the points that we're finding using this condition. If I find those points where it's 0, that's actually where the differential equation has a vertical derivative. Okay, so there's a vertical, not a vertical derivative, a vertical tangent line here. Okay, now that's not the case all the time, but when you're doing exact equations, especially if they have polynomial coefficients like this, it's because we have an implicit form that is polynomial, and so it excludes those options of corners or discontinuities of some sort. Okay, if you had something with like natural logarithm in it or something where there's naturally a discontinuity there or a place where it's undefined, then we're talking about something completely different. Okay, but this is a nice curve, and the place where you'd see this stuff, where we could have predicted this before, is basically something like this. So if we think about circles, okay, something like whatever, this guy, all right, if I found its explicit form, I have this idea where I'm taking roots again, right? I have a plus or minus and stuff. What do those two graphs look like? Okay, well, if you think about this, the plus root is this one, right? And then, so this is the plus root. And then the minus root is this one. Okay, that looks horrible. Sorry, guys. Okay, so where do these two things meet? Precisely at the vertical tangent line position. Okay, so that's kind of like exactly what we're doing. We could have predicted that we would have vertical tangent lines back at this step when we were getting the plus and minuses using the quadratic formula. Okay, it's the exact same thing when you're solving a circle. All right, so anyway, now that we have that, we're going to turn to MATLAB to find the actual interval itself. Okay, so here we are in MATLAB. We're going to find the interval of validity first. Okay, so I took our equation here and programmed this in here. The first thing was to graph it. I also graphed x equals 0, just to kind of, so we don't ruin the surprise. Okay, here's the graph. You can see from this graph, you can see this little white gap in here. It's cubic. Okay, it only crosses the x-axis once, and it's close to 1. Okay, so coming back here, we'll use f0 with our guess being 1, and then it's going to print the interval of validity. Now, coming back to the picture, it's positive from that point onward. Okay, the stuff under the radical. So it's whatever this number is to infinity is the interval of validity. So this tells it that I'm about to print a string in that position. And this thing, 8734, is the HTML code for the infinity symbol. Okay, so this is how you can get that in there if you wanted to, do that in MATLAB. Okay, so here it is, 0.98 stuff to infinity. Okay, that's the correct interval of validity. All right. Now, the next cell, I've just programmed in the differential equation just to check our answers and to look at what it looks like. Okay. So this is the answer. It's these things are both over 4. It's split it up. So it's x minus, and then this crap to the negative 1/2, or to the 1/2 power, so the square root of this stuff, which is exactly what we had. Okay. Looking back at the graph, here's the blue part is the solution. This dashed line indicates that it becomes vertical there, and that's why it stops. Yeah. Okay. So this picture kind of confirms what we were talking about. The negative root means it's the bottom half of something, and it does have a vertical tangent line at the point where it starts. Okay. So that's kind of interesting. Now, what I did down here, this is useful if you need to, like we did in the last video, I wanted to plot a whole bunch of different possible solutions with different values of c. Okay, in addition to the one that we had for our particular solution. Okay, just to kind of show you what all those solutions look like. Just looking at this picture doesn't really give you an idea of what's going on there. Okay, now, because I'm not going to constantly resolve it with c in there, I'm going to use the implicit form of the guy, and the function that plots implicit things is called f-implicit. The only kind of difference is that when you type in the function for this command, it needs to be set up in this way. It has to be something equals 0, and that something is everything else. So basically, in our implicit solution here, you have to move the c part over to the left-hand side so that it's equal to 0, and then that gets included in this guy. Okay. So anyway, I just did it from -5 to 5 in both directions, so you can see what's going on. I plotted a whole bunch of different things, and this is them. Okay. Yeah. So these are a whole bunch of different things. Notice there's all of these solutions which kind of go off to infinity, and then there's one that's contained in the middle here. Okay, we're going to be talking about that kind of stuff a little later. Anyway, the one we have, y equals 1, come up here. It's this light blue thing right here. It starts at this point and then goes down. Okay, so this light blue one here is the particular solution starting from here down. Okay, so anyway, so this is a good example. New function in MATLAB to use, which is very, very useful for this and the separable equation stuff. So use these as examples. And yeah, so now you got to see the graphical interpretation of everything. It did, in fact, all of these solutions have vertical tangents. This one has 2 of them. Okay. So all possible solutions to this guy is going to have a vertical tangent that's going to divide the interval validity into the upper and lower piece, and you'll have to figure out which one's which depending on the initial condition that's given. Okay. So anyway, so that's it for this example.